Okay, so we are in Statistical Rethinking, the second edition. We're in Chapter 8, and we're on question 8H4. Okay, so before you run any of this code, make sure that you install and load the Rethinking package with the code blocks at the top of this Colab sheet. Okay, so this is a long question, so it's all of this, but basically what we have is a data set that discusses or that has some data on 74 different countries, and among the variables here is the number of languages spoken in that language, the geographical area of the country, the population of the country, the number of weather stations in that country, as well as the mean growing season and the standard deviation of the growing season, referring to crops and things that they can harvest for food. Okay, and so the idea here, so we're going to test a hypothesis, and we're going to kind of do it in a stepwise fashion. But the hypothesis is that language diversity is facilitated by food security. Okay, so let me say that again. That language diversity within a country is facilitated or increased with increased food security, and so the problem gives kind of a justification for this, but basically, when food security is high, there is less need for large-scale social cohesion, and so that it allows for these little pockets of cultures to persist and therefore retain their languages and maybe not share languages across the cultures or something like that. So that's the basic idea. And so longer mean growing seasons we're going to use as a surrogate variable for for increased food security, right? So greater mean growing season means more food security. And then maybe another dimension of food security is the standard deviation of the growing season, right? So if you have radically different growing seasons from year to year, that might have an impact on perceived food security or actual food security, okay? And then finally, all of this is about language diversity, but we don't have language diversity in our data set, and so we're going to create language diversity by taking the number of languages of a country divided by the population of that country, okay? And so language diversity is going to be our outcome variable, and as defined here. And actually, what we're encouraged to do is to use the log of the language diversity. Okay, to use this, and there's reasons for that. The reasons are that there's probably better ways of handling this kind of data, but we don't yet have those tools. But we will develop those tools later on in the book. Okay. So let's kind of get going here. So the first thing I want to do is just to look at the data. And so here I have the data, and I've put in language diversity as well as log language diversity. I've just added these to the data set as well as log area. Okay, because we're sometimes asked to use log area as a predictor variable. Okay, and so this is what our data set looks like. I'm going to get rid of this summary. I don't think it's doing us any favors here. So let me run this again. So so here we have our data set, and then you can see the variables that we've added here on the tail of all of this, or on the rightmost columns. Okay, so so now we need to start modeling, but I am not an expert in any of this, and so I would have no idea how to begin assigning priors to anything here. And so the first thing I'm going to do is I'm going to standardize everything, okay, everything that we're going to use. So I just have my variables. I'm creating new variables with a underscore standardized there, and then using the standardized function on everything that I'm going to use. Okay, so I run that. Okay, and so now I'm going to push through a series of models here. Okay, and these models are roughly following what is being described in these suggested steps. Okay, so you can read through these for yourself, but basically we're entering one predictor variable at a time until everything is in there as well as an interaction. Okay, and so you'll kind of see what the pattern that I've settled on here. Okay, now there is a lot of advantages to, instead of just jumping to the most complicated model, which we have down here, to going about this adding one thing at a time. For one, when something breaks, if you have a simpler model and you've built it up from even simpler models, the number of things that could have gone wrong and therefore your troubleshooting is focused to very few things. Okay, so so even if we had no reason to worry to consider, say, this very first model, starting with it can be a good idea because it makes troubleshooting processes much easier. Okay, another advantage to building up like this is we can see how the inclusion or exclusion of certain predictor variables changes the inferences we might draw from our data and from our model. And if something is starting to produce very unrealistic or very unexpected results, then this might be a reason to go back, to retrace our steps and try to rethink what we're doing. So anyway, the way that I've done this is I just have an intercept only model, and then I add area, and then I have a model that corresponds to step A above, which asks us to look at mean growing season as a predictor. And then I have, to that very same model, I've just added area, log area. And then I have only the standard deviation of the growing season as a predictor variable. And then the next model, I add area to the previous model. Okay. And then finally, in the C models, of which there's 4, I have both mean growing season and standard deviation of the growing season. Okay. The first 2 models here have no interaction term. Okay. But then the last 2 C models do have an interaction term right here. Okay. And then within the first 2 models, they differ because only the second one of the 2 has area included. Okay, so you can look through all of those. But so these all run, and I've ran them. But then what we want to do is, or maybe one thing we want to do then, is to compare these models. And so I've compared them with WAIC as well as PSIS. Okay. And the results are very similar, so I'm just going to scroll down just so I can get everything in one window here. Okay, and let's just look at this. I'm going to just get rid of this just to free up some cognitive space. Okay, so the first thing to notice is that the C models, which again are the models that have both mean and standard deviation of growing season included as predictor variables, these are doing better than any other model, so that's interesting. Okay. The next thing to notice is that remember that MC66 and MC99, those formed the 2 models that had a interaction, and MC and MC33 did not have an interaction. So it seems that the interaction is doing some kind of work here, the interaction between mean and standard deviation. Okay, and then the other thing to notice is that within these 2 models, which again have an interaction, and these 2 models which do not have an interaction, the inclusion of area makes the models worse. Okay, so let me just kind of make that a little bit more concrete. Okay, so these 2 models performed best, MC66 and MC99. Okay, and MC66 did better, was predicted to do better than MC99, and the way that they differ is just the inclusion of area. Okay, and so adding area somehow made MC66 do worse, right? Because MC99 does worse. And then similarly, to go from MC to MC33, we just add area. And again, area is making the PSIS and WAIC worse. Okay, so somehow area is maybe not very helpful. All right. So now let's also look at the posteriors for these particular models. Okay. Ideally, we would be looking at these models at each, or these posteriors at each step along the way, but just to keep this video under an hour, you know, we'll just focus on these 3. So let's run these. Okay, so we have MC, MC66, MC99. Okay, in all of these, we notice that the mean growing season here is reliably associated positively with language diversity, with our measure of language diversity. So that's interesting. Okay. And we also see that standard deviation of the growing season is reliably negatively associated with language diversity. Okay, and so both of those ideas very much support the hypothesis that increased food security, reduces the pressures that would otherwise lead to a homogeneity of language, or less language diversity, I guess would be the better way to say that. Okay. And then we also see, so remember MC66 did the best, that's this model right here. We see that the interaction is reliably negative, both for both models that have the interaction, okay? And so what this is suggesting, right, is that with high enough variance or uncertainty or standard deviation of the growing season, even that means that certain countries with a high average growing season, if they have that have a long average growing season, if there's a lot of variability in their growing seasons, that they will perform worse, or they will have less. The effect on language diversity, they're going to have less language diversity than a country that has shorter average growing seasons, but is more predictable from year to year. So that's interesting. And then finally, area, just maybe as we could have deduced by the WAIC and PSIS comparisons, has a pretty ambiguous relationship with language diversity. So in any case, all of this, again, the fact that mean growing seasons tends to lead to an increased language diversity, and standard deviation tends to lead to decreased language diversity. All of that very much aligns with our hypothesis. But there's some caveats there. A major caveat being, okay, is this how we want to define food security, right? It could be that somewhere that longer growing seasons are not necessarily as productive as shorter growing seasons or whatever, but we're using growing season as a surrogate, and so our conclusions here are only as reliable as those assumptions. So if that's not a good surrogate, for example, then our conclusions are a little bit inappropriate possibly. So anyway, we'll call that good with this one.